Hi, we are Team Low Crane and we are doing our final project analysis on a tower crane. So this is a typical case scenario where a tower crane experiences loads due to its lifting the heavy load here. And so there will be forces here at front of the jib, and there will also be forces at the rear of the jib because of the counterweight. Additionally, the rotational platform will also exert rotational forces at the jib, and the base of the platform will also exert forces at the mast in order to keep the mast in place. This is our first case study of the original design of the rear of the jib with the material set to AISI 1010 steel. We performed a static study where the boundary conditions were placed at one of the end faces here. The load condition was 75,000 newtons and placed where the counterweights are, which is here. The results showed that the maximum stress was 68.8 megapascals and concentrated at the end here. The yield strength is also 180 megapascals. This is our first iteration of the design in which the thickness of the jib was varied at the rear where it experienced the maximum stresses, as you can see here. The boundary and load and material were all remained the same. However, the maximum stress was decreased to 68.4 from 68.8 megapascals. But the stresses at the end area was decreased to 11.4 megapascals. We then performed a closed-form solution of the rear of the jib in order to validate the simulation results. The model was simplified to be a cantilever beam with the same dimensions and boundary and load conditions, as well as the material. The hand calculations showed that the maximum bending stress was 74 megapascals, which is close to the simulation results, and the percentage error that we calculated was 8.18%. For the second case study, we performed a modal analysis on the front of the jib. The material was set to AISI 1010 steel, and the boundary condition was 4 fixed points at the joints connecting the rod, which is shown in the red as well as on the SolidWorks model. There was no loading condition because the study was modal, and the results show that the lowest natural frequency that the jib experienced was 7.16 Hz. We iterated the design by changing the tube sizes and comparing the results. The tube sizes were changed to 20 by 20 by 2, which resulted in 6.92 Hz, 40 by 40 by 4, which resulted in 7.16 Hz, and 80 by 80 by 5, which resulted in 7.87 Hz. Since a light earthquake generates around 1 Hz, we found that the bigger tube sizes are safer because it generates our natural frequency and it deviates from the chance of creating a resonance frequency between the jib and the earthquake. For our third case, we did a fatigue analysis on one of the jib connectors highlighted at the SolidWorks model part here. The material was set to AISI 1010 steel. There was a fixed restraint at the back outer face, as you can see on the green arrows. And there was an applied parallel load of 5,000 newtons at the two end faces here. The results show that the minimum cycles of the jib connector can endure 186,000 life cycles, which can be calculated to be around 100 cycles every day for approximately 5 years. For our fourth case study, we performed a static analysis on the base of the crane. In our initial design, we used 3D weldment features to make the beams of the frame. The base was simulated as a beam element. We faced problems while meshing the base, and therefore our simulation results were incorrect. The boundary conditions were fixed geometry on the bottom of the cement blocks, and the forces were along the diagonal beams. The maximum stress was 0.8 megapascals, located here, and the maximum displacement was 1.67 millimeters. For the first iteration of the base, the I-beam was created by using a sketch of the shape of the I-beam and then extruded instead of using the weldment feature in SolidWorks. This was done in order to avoid the interferences and meshing problems that we ran into while simulating the base. The part was simulated as solid bodies. The boundary conditions remained the same, but the load was changed to 7,000 newtons and applied to all the faces of the attachments that connect the base to the mast. The maximum stress is 618.2 megapascals here, and the maximum displacement is 480 millimeters. Part is very close to yielding, since the yield strength is 620 megapascals. For our second iteration of the base, we added supports for the diagonal beams to reduce the stress on the beams. The material, boundary, and load conditions were all remained the same, and the maximum stress that was resulted was reduced to 457 megapascals, and the maximum displacement was reduced to 289 millimeters. That's the end of our presentation, and thank you very much.